So thank you for coming to our presentation. We are Group 4. We created the UF7 Sabertooth. This team comprised of Tyler, Benjamin Bowie, Stephen Cantrell, Preston Daniels, Jessica Kong, Sergio Torres, Brandon O'Brien, and myself, Mark Wagner. And we can go begin our presentation.
So we were given the task of designing an affordable light attack aircraft capable of taking off and landing over a 50-foot obstacle within 4,000 feet when operating from an austere field up to 6,000 feet in altitude. The surface ceiling of our aircraft would need to be no less than 30,000 feet and had to operate with a 3,000-pound payload and required an integrated weapon system. The service life needed to be 15,000 hours over a period of 25 years, and the 2 crew members of the aircraft would need to be accommodated by 0-0 ejection sheets. So we also had 2 design missions, or 2 types of missions that our aircraft would be completing. One of them being the design mission, which is seen in the upper right-hand corner, and the other one being the ferry mission that can be seen in the lower right-hand corner. The ferry mission only required operation at 60% of the payload, while the design mission required operation with full payload. And it should be noted that much of our initial design decisions were based off the Beechcraft AT6 Wolverine and the Embraer EMB 314 Super Tucano because of their similar objectives for those types of aircrafts.
So the airfoil that the UF7 Sabertooth uses is the NACA 63A415. We chose this airfoil based on our initial weight and cruise speed estimations from the historical data. And then we realized that the NACA 63A415 using a trade study, that the geometry closely matches what is necessary to generate lift required at operating speeds while still minimizing drag. And the CL max for this specific airfoil is 1.5, and the coefficient of lift at alpha equals 0 is 0.4. So here's the model of our wing, the shape, and our plane flap that are on each wing. The plane flaps were included to increase lift and loiter because after some analysis, we did realize that the airfoil we chose probably could not generate enough lift at this point without a high lift device, but with the plane flap, it was able to. Now, when we are actually considering the dimensions of our design, we use historical data to find these parameters. Our wingspan is about 35 feet with a wing area of around 156 feet squared. And we realized that according to historical data, that the aspect ratio that we should use would be something like 6.945. And the taper ratio that we wanted to use for the wing was 0.55, which aid in achieving the optimal wing lift distribution. Now, the chord at the root is about 6.13 feet, and due to this taper ratio, the chord at the tip is 3.37 feet. We also determined that it was necessary to include a wing sweep and a wing dihedral to help with lateral stability. We also have gone with a low-mounted wing on the Sabertooth to allow for landing gear to be conveniently stored in the wings, and also to allow sufficient clearance for our payload. Lastly, the UF7 Sabertooth utilizes cutoff wingtips. This is because at the speed that we're flying at, which is around Mach 0.42, the effects of wingtip vortices will not necessitate another design of wingtips, which would be heavier and would increase costs. So using these cutoff wingtips will lower costs, minimize weight, and minimize drag.
So now onto the propulsion of our system. Our engine was required to produce at least 1,500 shaft horsepower. This was based off the calculation between the takeoff weight of 10,159 pounds and the takeoff thrust to weight ratio of 0.1313. After going through a few different engines and scaling them for comparison, we found that the PT6A68D was right within what we wanted. It produces 1,600 shaft horsepower, just a little bit under what we needed, providing a nice safety factor as well. We would go with a tractor configuration, allowing us to put our propeller in front, ensuring that it was able to have maximum efficiency due to nice, clean, undisturbed air in front of it. This now leads us into the propeller design. we went with a diameter of 9.262 feet. We also had 4 blades, as you can tell. This allows us to maximize the thrust that we get from the engine, the 1600 horsepower. And we designed it with 2 RPMs in mind, 1190, which would be 70% of the max, and then the 1700 max, which would be required for takeoff and landing. Taking into account the Mach velocities, the Mach 1 of the tip velocities, and keeping our design under that, we minimize it a little bit, finalizing it to the diameter you see now.
So our fuselage was calculated to be 33.6 feet in length. And from that, we determined the fineness ratio could be practically set to 8:1, which meant that our largest effective diameter would be 4.2 feet. And then the crew station, which would be within the fuselage, we decided to go with the Martin Baker MK16 US 16 LA ejection seats. The crew members would then be seated in tandem configuration, and the crew station would be 145 inches long with 33 inches between the 2 edges of the canopy of the crew station for ample operating space. And the grazing angle from the crew station seats would be 30.25 degrees with a look down angle of 40.3 degrees. And here are the basic geometric parameters for tail. A conventional tail design was chosen for our plane. And we decided it would be located at about 2.75 wing chord lengths from the quarter chord of the main wing and 0.25 wing chord lengths above the center line of the wing. For the vertical tail and stabilizer, the GOE411 airfoil was chosen because it is symmetrical, and the vertical tail specifically would be offset a few degrees to suppress propeller wash.
For the landing gear, several key design choices were made that influenced the overall design of the landing gear. For the Sabertooth, it was important to have retractable landing gear. This reduces drag when compared to fixed landing gear, and it makes the aircraft harder to detect, improving stealth characteristics. Due to the generous space available under the wing, as previously mentioned, it was decided that the main gear will retract into the wing. Of the various landing gear configurations, it was determined that the tricycle design with 2 main gear after the center of gravity and 1 nose gear would be best for this aircraft. Opposed to other designs, such as the tail dragger, this configuration is the best for the Sabertooth as it operates out of austere fields, where the tricycle configuration will help with ground stability. The landing gear will also use oleo shocks to support the weight of the aircraft and dampen the landing forces. The main gear typically support around 90% of the gross vehicle weight. The landing gear that we decided to use for the Sabertooth used Goodyear 8.50-10 tires. These tires have a diameter of 25.65 inches, and they will utilize a pressure of 50 psi. These tires can support a static load of 5,500 pounds, which provides a great margin of safety for use on the Sabertooth. These tires were also rated for landings at 160 miles per hour, which based on our calculations was ideal for the Sabertooth. The oleo shocks of the main gear must dissipate a significant amount of energy upon landing, so calculations from the Raymer textbook and from other resources were used to determine the correct oleo shock sizing. The oleo shock for the main gear will have a total length of 21.65 inches with a stroke of 8.7 inches, and the diameter of the oleo shock will be 2.4 inches. This is all based on the internal pressure of the oleo shock being estimated to be 1,800 psi, which is a pretty standard estimation. The nose gear of the Sabertooth will use Goodyear 7-6 tires, which have a diameter of 18.75 inches, and these will be inflated to a tire pressure of 32 psi based on our calculations. These tires are rated for 3,600 pounds static load and 160 mile per hour landing as well. The nose gear will also use an oleo shock to dampen the landing loads, and it will be that same 21.65 inches long, but this one will be a slightly smaller diameter, coming in at 2.3 inches. It is important to note that these tire pressures are designed to be suitable for austere field conditions. According to Raymer, the maximum tire pressure allowable for landing and takeoff from runway surfaces such as a tarmac in good condition, temporary metal runway, and dry grass on hard soil are all less than 60 psi, which these tires are rated for. This is ideal for the austere field conditions that the Sabertooth is designed for. Shown here is the tricycle configuration and the wheelbase dimensions. These locations were chosen for ideal stability while making sure that the tail of the aircraft does not strike the ground during tip back, and that the wingtips do not strike the ground during a 5-degree roll. These all comply to regulatory guidelines. The overturn angle for this configuration was also designed to not exceed the recommended 63 degrees, and in this configuration it comes in at 55 degrees. It can also be seen here that the nose gear is sufficiently clear of the propeller. Next, let's discuss the structure of the aircraft, starting with the wing structure. The wing structure for this analysis was modeled as a box beam. This was done for the relative simplicity of the analysis, as well as the structure having good historical use in aircraft. The geometry of the wing box was constrained by the predetermined size of the wing and the flaps, with the only parameter that needed to be adjusted coming from the wall thickness of the box beam. The box beam structure must support the entire lift that the aircraft generates during flight, with most of the stress in the wing box expected at the root. This wing box must be designed to not only resist failure from the stress, but failure from fatigue and cracking. As with all aspects of aircraft design, weight is an important issue. So while the strength of the wing box must be designed to resist a sufficiently large loading, it should not be designed to be too strong, which will add unnecessary mass. When designing this wing, a factor of safety must be determined to ensure that the aircraft is safe to operate throughout all flight conditions. To analyze this structure, the finite element analysis software Abacus was used. The wing box was modeled in software as a shell with varying wall thickness. The goal of this analysis was to determine the ideal wall thickness for our flight conditions. Only half of the wing box is analyzed in this model, since it will be identical loading on the other side of the wing box. This wing box measures 25 inches wide by 9.4 inches tall and 16.5 feet long. The wing box boundary conditions are similar to a cantilevered beam, since the structure will be fixed at one end, the root, and it'll be free along the rest of the beam. A line load was applied to the wing box, acting at the quarter chord of the wing. This is a good estimation of the load distribution expected on the wing box, despite being a simplification. This line load was also modeled to be elliptical, with the majority of the load occurring at the wing root and a significant drop-off towards the wing tip. This analysis also splits up the load to have 1/3 of the total force acting on the bottom surface and 2/3 acting on the top surface. This is, again, another good estimation for what forces will actually occur on the wing box to give us better results. The model view of this analysis can be seen on the upper diagram of this slide, and you can see that the line load is elliptical. The total force acting on the wing box, it was calculated to be the total takeoff weight for the design mission, which is a very conservative estimate, and it's just under 11,000 pounds. Finally, the material chosen for the wing box was aluminum, specifically 7075 T6 alloy. This is a great structural material due to its high strength to weight ratio and easy repairability compared to composite materials. The results of this analysis showed that the best combination of wall thicknesses was to use 1/8 of an inch on the sides and 3/32 of an inch, or around 94 thousandths of an inch, on the top and bottom. The top and bottom panels will experience lower relative stress than the sides, which is why they can be thinner and reducing the weight without sacrificing much strength. While this combination of wall thicknesses, with this combination of wall thicknesses, the maximum stress that occurs in the wing box is estimated to be 42.1 KSI, which is significantly lower than the 64 KSI yield strength of 7075 T6. This results in a factor of safety of 1.52, which is great for aerospace applications. Further analysis on this wing box was performed in MATLAB, which analyzed the shear flow around the wing box as well as the different failure modes of the wing box. This analysis showed that the maximum allowable crack length was 0.68 inches if there was a crack at the bottom section of the wing box near the root. This would, of course, be an area of concern during all inspections performed on the aircraft, so we'd have to take special care to monitor it. The stress analysis also showed that the aircraft has a fatigue life of over 5 million cycles, which is acceptable for an aircraft with the service life of over 25 years that the RFP asks for. Finally, the fuselage structure was modeled in SOLIDWORKS to demonstrate the Semi-Monocoque Design. This design uses ribs and spars to support the entire aircraft, with the skin attaching on this design. The structure is easy to manufacture and repair, as it uses 70-75 T6 aluminum for its high strength to weight ratio again. Currently, you can see each rib is separated by around 15 degrees, but this can evolve over further design analysis.
All right, thank you, Mark. So materials on the aircraft. The Sabertooth is mainly comprised of metal alloys rather than composite materials, even though composites are becoming more and more common in modern aircraft. The reasoning behind that is because composites are more difficult to repair, especially on a light attack aircraft, which is expected to see some combat throughout its lifetime. So it's harder to match the strength and stiffness when patching parts of the aircraft. Obviously, we don't want a patch that's too weak, but also having a patch that's too strong can cause excessive deflection in the surrounding areas. So for the skin of the aircraft, we'll be using 2024 T3 aluminum. 2024 is soft and easily manufacturable with a high fatigue resistance. And we found that it's pretty much the skin standard for aircraft, still using more metal alloys rather than composites. As Mark mentioned, we're also going to be using 70-75 T6 aluminum. It's got a high strength to weight ratio. So we're going to be using it in the wing box, as Mark mentioned, and also adjoining sections to the fuselage. Titanium is also a highly desirable material, again, for its high strength to weight ratio, but its capability to resist heat. Because of that, though, it's also difficult to manufacture, but it makes it ideal to be used around the structure of the engine, where we expect high temperatures to occur. And finally, we have the propeller, which will be made out of a composite. Our reasoning was because it has a smaller surface area, so there's less risk of it becoming damaged in combat. We can reduce weight with this composite and thus have a lower stress on the engine. It was kind of difficult to find information on composites and propellers online, but we did find one company, Hartzell, which uses a nickel cobalt leading edge on their carbon fiber composite. The reasoning is it's to deter against erosion, and the Sabertooth will follow in a similar fashion with that.
So to fulfill its role as a light attack aircraft, our Sabertooth aircraft is capable of carrying a variety of weapons. Overall, our team selected a total payload of 2,704.8 pounds. And the weapons that we included were selected based on historical research for the weapons utilized by other light attack aircraft in a similar class. These attack aircraft included the AT-6 Wolverine and the A-29 Super Tucano. So our resulting payload included 4 GBU-49 500-pound laser-guided bombs. These bombs are going to be very effective in neutralizing heavily armored targets on the ground. Our payload also included 2 AGM-114 Hellfire missiles, which are sort of the go-to air-to-ground missile to neutralize medium armored targets on the ground. And then our aircraft also includes 14 GATR 2.75-inch laser-guided rockets. These are 7 laser-guided rockets mounted under each wing, which are intended to neutralize light armored targets on the ground. And then aside from the explosive payload of the aircraft, there are also 3 integrated guns. This is part of the RFP requirement from AIAA. These guns provide the Sabertooth with an alternative method of neutralizing enemy targets on the ground, as well as enemy aircraft. To select these guns, a trade study was performed with some of the highest weight factors, including the weight of the guns, as well as the muzzle energy and recoil force of each gun. And as a result of the trade study, we selected 120 millimeter nose cannon, the NC621, and that's going to be mounted underneath the center line of the aircraft under the fuselage. as well as 2 HMP 450 caliber machine gun pods, with one being mounted under each wing. Again, the inclusion of these integrated guns just simply diversifies the Sabertooth's role as a light attack aircraft.
For the weight estimation, we looked at historical data and background research to determine the weight of each subsystem. So for propulsion, we had 806.4 pounds, and that includes stuff like the engine, gearbox, propeller, and housing. For structures, that came out to 2,092.4 pounds. That includes the frame, wing box, struts, skin, and tail. For our equipment, that's auxiliary units, so the auxiliary power unit, avionics, flight controls, pneumatics, hydraulics, any other auxiliary systems that we have, that came out to 1,560 pounds. And armament, which came out to 3,414.8 pounds. That includes our bombs, missiles, rockets, and integrated guns. Add all those together and you get an empty weight of 7,873.5 pounds. You add on the useful load of 3,086.3 pounds, which includes fuel, oil, ammunition for the integrated guns, as well as the weight of the crew and their equipment. And you get a total gross takeoff weight of 10,959.8 pounds. That's 2,300 pounds less than what our initial estimations were for this. And for our center of gravity estimation, once we had the weight of each subsystem in our aircraft, we used SolidWorks and historical data to estimate the approximate location of each one. Using that, we could determine the center of gravity of the aircraft. So if you, as you can see here, our X direction center of gravity is almost exactly along the quarter chord line of the aircraft. And then our Y and Z center of gravities are almost exactly along the center line of the aircraft. For the X direction center of gravity, when we drop our payload and use about 60% of our fuel, our center of gravity shifts back aft 8 inches, and then it shifts upward in the Y direction by about 6 inches after a full payload drop.
Okay, so longitudinal stability. There's a lot on the screen here, but we followed along with the Raymer textbook and we analyzed the wing, the horizontal stabilizer, the fuselage, and the propeller. And when we're looking at longitudinal stability, we're mainly concerned with CM alpha, or pitch moment due to angle of attack. What we found is at empty and full, we have negative values, which means our plane is stable in the longitudinal direction. So if a gust were to hit our plane and we have a pitch up moment, our plane would attempt to return back to center and become neutral and stable again. We also have a static margin, which is just the distance between the neutral point or the point where CM alpha is 0 and the center of gravity. And that does shift because of our center of gravity shifts when our weight is changed. We also have here flap deflection. So at cruise, our aircraft will not require any flap deflection. We have enough lift to keep it level at trim. At takeoff and landing, though, we will require 13.3 degrees in order to create enough lift for those scenarios.
Now on to lateral directional stability. Similarly to longitudinal stability, we used the Raymer textbook to calculate this. The structural components that we used to that we needed to consider for this was the fuselage, the vertical tail, the wing, and the wing dihedral angle. Now, the roll moment that we calculated due to side slip, that was negative 0.138, which would make our design stable laterally. And then the yaw moment due to side slip was calculated to be negative 0.024, which makes our aircraft marginally unstable directionally. But this would be able to be minimized through the use of autopilot and the pilot being careful. Then we have also had to ensure that a design satisfied the crosswind landing lateral trim conditions, which was a crosswind with a side slip of 20 degrees. It was determined that our ailerons could deflect negative 15 degrees and 96 degrees to stay stable in these conditions.
For our performance, once we knew the lift characteristics of the wing, the weight of the aircraft, and the thrust that it generated, we could determine the range and the endurance of the aircraft, which is 3,137.6 nautical miles and 12.78 hours, respectively. These are both well within the requirements for the RFP. After we did that, we determined the cruise rate fraction, which is the weight of the aircraft at the beginning of the design mission over the weight of the aircraft at the end of the design mission, which is 3.065. Once we found that, we did the takeoff and landing distances as well. These are at the worst case scenarios where the aircraft is at austere landing fields and 4,000 feet above, or 6,000 feet above sea level taking off. As you can see on the right here, our landing distances are at 2,900, or our takeoff distance is at 2,901 feet and 3,790 feet. On the right, we have representations of the takeoff and landing distances. For our performance, we calculated our cruising speed to be 322 miles per hour or 472 feet per second. We picked a cruising altitude of 25,000 feet. And once we did that, we were able to find the stall limit and maximum dynamic pressure lines. From those, as you can see on the right, we maxed out at around 34,360 feet, which ended up being our service ceiling. And then using those lines, we were able to approximate where the aircraft made zero specific power. And you can see those on the right in the operating envelope graph.
So our team performed a thorough cost analysis to determine the overall affordability of our design. We calculated various costs with some of the most important values, including the RDT&E, as well as the flyaway cost, the cost of fuel, maintenance, and consumable goods, as well as the crew salary. Each of these costs were considered over a yearly basis, which included 1,200 flight hours per year. And two scenarios were considered. The first scenario being obtaining a single Sabertooth aircraft, and the second scenario being obtaining a lot of 50 Sabertooth aircraft. Some of the most important values for the single aircraft were a total flyaway cost of $13.5 million per unit, as well as a cost of fuel and maintenance of $494,000 and $463,800, and then a consumable cost, which includes oil, brakes, and tires for the landing gear of $20,700 per year, and a crew salary of $107,640 per crew member. So after our initial design was complete, our team was interested in determining the alternative configurations that our Sabertooth could exist as. So we generated 3 carpet plots that analyzed the relationship between the gross takeoff, or between the wing loading and thrust to weight ratio of the aircraft. So selecting a thrust weight ratio and wing loading parameter of 10% less than our ideal design yielded an alternative configuration of an aircraft with a takeoff weight of 8,900 pounds and a takeoff distance of 1,700 feet. Whereas if we increased the thrust weight ratio and the wing loading parameters by 10%, then an alternative configuration existed with a takeoff weight of 13,000 pounds and a takeoff distance of 12,000 feet. As we know, one of the RFP requirements for the light attack aircraft was to include a takeoff distance of less than 4,000 feet. So this alternative configuration with a takeoff distance of 12,000 feet wouldn't exist. It couldn't be possible for our design. So yeah, in the end, this was just a good analysis to determine the alternative configurations of our aircraft.
All right, just want to say thank you for listening. We appreciate you taking the time out of your day to come and listen to our presentation, our aircraft. I know it's a little weird in these trying times with being on Zoom, but looks like things are going to be back to normal in a little bit. But are there any questions?
Oh, we have several visitors here. Thank you for coming to our presentation. So do you have any question, comments, suggestion, anything? Great job, everyone. I really enjoy your presentation, the slides and the presentation yourself. I can feel that you are very passionate about your design, and also the whole presentation is very logically collected, and the slides are very pleasant to read. It's very clear information here. And again, as a super picky person, here are some comments, some small points that I want to make some suggestion. So the first one is that at the very beginning of the presentation, you have the design requirements. That is from, let's say, AWA requirement, and then you start from the L for your design directory. So I would suggest that based on the requirements, we put the initial estimation information here, right? Because the procedure-wise through this semester that we have the requirement that is the same for every group. And now using the requirements, we don't have anything designed. We have the initial estimation of the weight, thrust to weight ratio, wind loading, and lift drag ratio, things like that. And then we use this estimated parameter to guide our design for the wing design, tail design, fuselage design, landing gear, everything, right? So I would think that it'd be nicer if you can add one slide to put the initial estimation result, like what is the weight, what is the lift drag ratio, thrust to weight ratio, and wind loading there, and then start our wing design, tail design, fuselage design, everything. So that is a suggestion. And the second thing is on the fuselage and crew slide, there's no page number. So could you please change it to fuselage and crew. So there is a look down angle, 40 degrees. So what angle is that?
That's the angle where you look down off the side of the aircraft.
Side angle, okay.
Yeah.
Okay, great. So I would also suggest that you put the visual angle over the nose here, because that is also a very important property of the cruise station design. So, and the next thing is, it's not something wrong, but in the wind analysis, I'm just curious. How did you calculate the allowable crack size, 0.686 inch?
That's a great question. So
You want me to take that, Mark?
Oh yeah. Wait, you want it?
You want me to take it?
Sure. Yeah. I think Tyler worked on it more.
So I guess it's kind of weird. We have a MATLAB script from structures, and it was a wing box design. So we basically just adapted it for our parameters and our dimensions to figure that out.
Great, thank you. So I'm just curious. There's nothing wrong there. And the next one is, I feel that the payload you gave here is 2,700, but requirements is 300, right? But 3,000. Is that right?
I believe the requirement is 3,000. The way that I interpreted it, I thought it was a maximum payload, like it could not exist or it could not exceed 3,000 pounds. Not that it was a minimum 3,000 pounds. So I may have misunderstood that.
So I'm not sure my understanding is correct. So what I feel is that when the requirement is 3,000, we would better, well, there's no way we can make like exact 3,000. I would prefer to have a little bit higher than 3,000 to show, okay, my aircraft can satisfy all the requirements, even if we carry more than 3,000 pounds of payload, right? So that's like more persuasive of our design. And the next thing is the longitudinal stability. Next slide. So the flap deflection angle is 13.3 degree for takeoff and landing. So is this flap deflection is the same for takeoff and landing? Okay, so not necessarily wrong, but my personal opinion, what I feel that the flap deflection of landing should be a little bit higher than takeoff. Because of course, both takeoff and landing, the speed is low. We need to use the deflection of flap to increase the lift coefficient. But we also should be aware that during the takeoff, we need acceleration. And the flap deflection, if it's like to fully extend it to the maximum flap deflection, it will cause too much drag.
Right.
So it will not good for the acceleration in a short distance to lift off, right? But during landing, it's a different story. During landing, we just want to cause as much drag as we want, right? There's nothing to worry about that for deflection of the flaps. The large angle flap deflection will cause like too much drag or anything. We want that drag. So I would normally consider that the flap deflection during landing is a little bit higher than takeoff.
Okay.
Yeah, just some small suggestion. And next slide. So the derivative of the role of the yaw moment with respect to side slip, I would still suggest that you try to make it positive for your final report, because it's hard to say that we just want to make the pilot more careful during the flight, because then your pilot will be super tired during the whole flight because they need to keep control for put a lot of effort for the lateral stability. So try to modify your design a little bit and see if you can make this one positive. And another thing is that the crosswind landing trim, and there is the angle 96.64 degree. So is that angle too large?
Yeah, I think that's something we need to go back and reevaluate.
Yeah, it's definitely like too large deflection. So so double check on that. And so that's it. So that's all my comments. But overall, really great presentation. I really like it. I enjoyed the whole process of the presentation. So any other comments? Okay. Then if no other comments, thank you for all the visitors come to our presentation, support our groups. And thank you for all of you giving us this wonderful presentation today. And congratulations, and good luck for your final report. Keep working.
Thank you.
Thank you.
Yeah, thank you for coming.
Thank you.
Remember to go check out our video because it's great.
Thank you.
Thanks.
Thank you.
See you, everybody.
Bye.
Bye, everyone.
Bye.